So welcome everybody to our webinar, Clear Skies to Stormy Seas. And this is the first of two webinars this evening. And the one after this will be an advanced webinar, but this first one is our introduction to weather. Just make sure I've got that. And my name is Hugh Marler. My wife was unable to attend today. She had surgery earlier this week, so I'm acting as her stand-in, and so we'll get started here and go through some essentially some initial introductory topics, and then I'll turn it over to Alex. Before we get started, though, if you could please mute your audio, and that way any background noise won't get into be heard by others. If you have any questions at any time, feel free to use the chat. We are monitoring the chat so that we can answer questions that you might have, and then we certainly there's a Q&A at the end, and we can answer questions there. Again, if you want to turn your video on, that would be great. It's great that everybody can see everybody else. And then we are recording this, and that we will be sending a replay link out, and also a special gift for those who provide their email and their contact information. So before we get to our presentation from Avix Avalos, who's from WRI, which is Weather Routing Incorporated, if you don't mind, I'd like to have a few of you, if you'd like to kind of get an idea of who is on and what your interests are. In the chat window, you can type in some answers to these questions. For instance, do you own a boat? If you do own a boat, how old is your boat? Do you currently have insurance on your vessel? What is your experience level? What kind of sailing or boating do you do? In other words, offshore, onshore, both, day sailing. And then what are some of your biggest concerns about being on the water or the ocean or lakes? And specifically, what concerns do you have about weather, and what you're looking to learn about weather? And again, you can put those answers in the meeting chat. And if there's even just questions you want to ask in the chat, you can do that as well. A couple of the things that we're going to talk about and sort of what we're trying to accomplish here on this presentation is the idea in this webinar is to provide you a good, solid, basic understanding of weather, so that when you see weather on TV or on a YouTube channel, that you have an understanding of what they're talking about and why they're talking about it. Perhaps some of the words they're using, some of the diagrams they're using. You might, there be, when you see a certain cloud formation, what does it mean? What's it telling you? Is it telling you that a storm's coming? Is it telling you a storm's going away? Clouds, and Alex will talk about this, they can tell a story. So it's always good to learn about that. And then also, when you hear U.S. Coast Guard alerts, they use a lot of terms that relate to weather in those, especially if you listen to the VHF weather channels. So it's good to understand those aspects. And then, it's always good to remember that these days there's, many ways to connect to the internet from your boat. And this is important because things like Starlink or SIM cards and mobile phones, they provide you real-time access to weather information. Rather than having to wait a long time before you get that information, you can see it in real time and get updates. So you might be out on the open ocean and need a weather report from WRI. Well, something like Starlink, you can get that right away rather than waiting several hours. And again, things like the Coast Guard alerts and cloud formations, these are, resources and information that you can get. And then of course, there's lots of apps that take raw information from NOAA and other sources and allow you to see them on your phone or your tablet, such as Windy or Buoy Weather, Predict Wind. And, in addition to connectivity options such as Starlink, there are satellite messengers, which are for geosynchronous satellites, things like the Garmin InReach and the Somewhere Global Hotspot. And these devices can get weather information. They can even send and receive text messages. And so they're really useful to have as another way to get weather information. And then again, the different sources and applications, like, of course, NOAA, which is, the National Oceanic Administrative Administration, Marine Weather Center, Chris Parker, Marv's Weather, Buoy Weather, WRI, and then apps like windy.com or Predict Wind. And as what most sailors will tell you is that, the best approach generally is to have multiple sources, not just one source, but multiple sources, and then you can compare the two to get the most accurate or confident predictions that you can. And so with that, I'm going to turn it over to Alex Avalos, who's the senior meteorologist at Weather Routing. Alex, so I'll turn it over to you.
Sounds good, Hugh, and thank you for the introduction. Let's go ahead and dive right in. As Hugh said, my name is Alex Avalos. I'm an operations manager and senior meteorologist here at Weather Routing Incorporated. And tonight we're going to focus on two components. The first one's going to be more of a nuts and bolts discussion, basically how to interpret a surface analysis, also interpreting radar and satellite. We'll also go over some other details as far as buoy data and how you can use those to better understand the weather surrounding your locations. So a very brief overview about myself. I have a bachelor's in science and atmospheric science. I attended Linden State College in Vermont and graduated a little over 11 years ago. For those who are familiar with Northern New England, in Northern Vermont, it's also known as Vermont State University, Linden today. Basically, what I've done here at Weather Routing is, as an operations manager, I have overseen the growth and development of my peers, and I work closely with them to provide them the guidance and the leadership that is necessary to help them continue to see their growth within the company. As far as my experience with sailing, we are located in upstate New York, about an hour north of Albany, the state capital, and we have a local lake called Saratoga Lake, where we have taken courses to get a better understanding of best wind angles and when to recognize, approaching weather and how to recognize that, and the actions that you can take to, best take advantage of the wind angles, such as through tacking and even jibing. But this class has given me real life opportunity to better understand the effectiveness, so that way I could assist with providing forecasts in real time to our clientele. A brief overview about Weather Routing. We were founded over 60 years ago by a gentleman named Bill Kasich. Believe it or not, the company did start in New York City originally, but over the years, it's worked its way up the Hudson River, and now here we are, an hour north of Albany in Glens Falls. We specialize in a number of areas. I'm an operations manager in our yacht division, but we do also have a commercial division. A little bit more about what we do on the yacht side. We provide forecasts for motor yachts, sailing yachts, sport fishers, jet yachts. We also do specialized forecasting for marinas, as well as races and regattas, fishing tournaments, and other various yacht rallies. A brief overview of our commercial division is that they forecast for container ships, cruise ships, as well as tugs, and also other commercial vessels, with a focus on marinas that particularly focus on larger vessels, for those areas. So some of the topics we're going to cover tonight, again, as I said, this is more of a nuts and bolts discussion. The first part of the presentation will include discussions on interpreting the differences between weather and climate, as well as surface analyses. We'll also go over how to interpret current observations through buoy and ship data, as I briefly mentioned at the beginning. We'll also include a more detailed discussion on radar and satellite. At the very end of the discussion, we'll talk more about currents. Of course, they're not necessarily a phenomena driven by weather, but the weather definitely has a very real effect on them. But they're also very important to understand when it comes to a successful or an unsuccessful sail. So we'll have more information about that at the end of the first presentation. So you might wonder, what drives all weather? Well, It's that big orange fiery ball in the sky, the sun. Obviously, we think about the sun, it's a heat resource to the planet Earth, but it does, in fact, govern our weather patterns around the world. And without it, certainly, things would be more chaotic in nature with respect to, you know, with respect to that. But in addition to it driving our weather, obviously, of course, it does help to keep our planet inhabitable, to all forms of life. But the ways in which the sun does affect our weather involve the short wave radiation that emanates from the surface of the sun towards planet Earth. Now, because planet Earth is obviously a sphere, and it is round, the radiation that is inbound from the sun is going to have disproportionate effects when it reaches the surface of the Earth. So, the equator, of course, is the hottest location on planet Earth because of its direct angle with the sun. But of course, the poles are more subject to indirect radiation receipt. And because of that, they're going to be more subject to various seasons. So think the further away you get from the equator, the greater variation there will be, in terms of the seasons around planet Earth. So Northern Hemisphere is heading into the winter season here in the coming weeks, and the Southern Hemisphere will be emerging from spring and into the summer season. So equator receives the most radiation from the sun, the poles receive the least amount. So what happens after it reaches the surface of the Earth? Well, the heat from this radiation is redistributed. So what happens is it's redistributed from the equator towards the poles. And because it's most direct at the equator, that's the heat that's working poleward, while at the same time, cooler air from the poles is emanating towards the equator. And that basically creates a boundary. And what those boundaries are basically are air masses. Heat is redistributed from the equator to the poles, and cool air is redistributed from the poles to the equator to create more of a balance. But that results in air masses. Now, as far as the overall strength of the air masses, it's not one size fits all. They can vary in strength and magnitude. Southern latitudes, and we'll use the northern hemisphere in this example, and we'll use North America. Southern latitudes of North America tend to see the tropical air masses, which are humid, moist air masses, whereas further north across Canada, for example, you tend to get drier, colder air masses, with the exception in coastal areas where those air masses tend to be more maritime in nature and more moisture. But basically, the convergence of these air masses gives way to, our fronts. And what happens is when we do get those fronts, you tend to get storms. You can get significant changes in temperatures over short distances and short periods of times. But generally speaking, in terms of the fronts, the best way to measure the strength of it is to take a look at the temperature gradient on either side. So if it's a very large gradient from one side, say it's 80 degrees ahead of the air mass, but on the back side of the front, it's in the 40s or 50s. It's a pretty strong system because that's a 30 to 40 degree temperature difference. When the difference is smaller, usually the weaker the front. But the movement into and out of these air masses is what produces and drives our weather. I'm going to briefly turn it over to a quick discussion about climate and weather. So there's multiple categories on the Köppen-Geiger climate classification. Basically, what happens is climate is the average of weather conditions over long periods of time, over hundreds of years. And when you look at this image, you can clearly see that, the warmest locations are generally near the equator. Those are what we refer to as equatorial climates, and they span from Ecuador across northern Brazil and across Central Africa, as well as across Southern Asia. But the further away you get from the equator, you'll note that the climates also gradually cool off. So they go from arid to warm, warm to snow, and then snow to polar. Obviously, polar climates tend to be located closer to the poles. But more northern latitudes in the northern hemisphere and the most southern latitudes in the southern hemisphere tend to be, the coolest air masses or climate locations in each of those areas. So weather tends to focus on what's happening in the shorter term. Climate takes a look at what's happening over the course of hundreds of years. And for the weather, what I mean by shorter term is we're usually looking at the average of 1 to 2 weeks. So now we're going to go into a bit more of a discussion on surface charts. There's a wealth of information that might sometimes be overwhelming to the person who is looking at one, but they include a very important array of images of the features that might be affecting a given region. So most commonly, you'll see areas of high and low pressure. You'll also see cold fronts and warm fronts, as well as any tropical systems that might be ongoing, as well as troughs. Really briefly on that, there are similarities and difference between cold fronts and troughs. I will get into that discussion a little further into the presentation. But basically, to tie it all up, having a knowledge and understanding of surface analyses can allow anyone who's looking at them to construct a self-weather briefing to better gauge what's happening in the present and how that might affect what's happening in the future. So further to what I said, as you can see in this surface map as an example, of course, there is a wide array of information from the numerous fronts that are in place across North America. Just as an example, there's a strong front that's extending from Ontario into the northern high plains, extending from a strong gale, which is a strong area of low pressure over Hudson Bay, and then a warm front extending down into Quebec. Areas of weaker low pressure you can see are dotted across the lower 48 of the United States. These brown dashed lines tend to indicate troughs of low pressure. These solid dark brown lines indicate pressure, in a given location. And generally, the more compact the isobars are, the stronger the winds are, or the stronger the system. But I'll go in more detail about that here shortly. So we're going to start off with the calm and favorable weather before we get into the less favorable weather to talk about. Areas of high pressure. These tend to be more permanent over a given location. For example, the subtropical high and ridge that parks over the central Atlantic during the summer months. Usually stronger ridging extends outward from the high. And one of the other phenomena that tends to happen, especially this time of year, is we see that ridging building in across much of the Caribbean, the Bahamas to the Virgin Islands, as well as the Windward and Leeward Islands. And that's a phenomenon that we call Christmas trades, given that they tend to ramp up in the weeks ahead of Christmas. But it's a very stagnant pattern and can really persist for longer durations of time. But as far as the highs themselves, like I said, favorable weather tends to be present in the center of these highs. They tend to rotate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Winds are calmest near the center of the high, but as you get into that stronger ridging, think the Christmas trades, the higher winds tend to be in place there. Usually within areas of high pressure, at least in the center, you'll tend to see minimal cloud cover. So, if you're in a region where winds are very light and there's minimal cloud cover, odds are very good that you are in the midst of an area of high pressure. So you can see here in this example, there's a broad high across southeastern Quebec and into New England. But note that the isobars are very spread out. So that's going to allow the winds in this instance to be very benign across southern Quebec into New England and New York in this example. Now, turning to less favorable weather conditions, and certainly something that when you are out on the water, you'd want to be aware of are areas of low pressure. So basically what these are the opposite of high pressure. You have the lowest pressure in the center, whereas in the high, you have the highest pressure in the center, and then it lessens the further away you get. But in the case of low pressure, it's lowest in the center, and then it increases outward from the center of the low. And it tends to be most unsettled and stormy in the low center. But think that, a deeper system tends to be more intense. In that case, isobars will be very tightly packed as opposed to, more loosely. Stormiest near the center, and in the northern hemisphere, they rotate counterclockwise, and in the opposite is true in the southern hemisphere, where they rotate clockwise. So here's an example of an area of low pressure in the lower Mississippi Valley of the United States. Note how the isobars tend to be a bit closer together, so that indicates that there's unsettled weather. In this area between the cold front and the stationary front to the north, you tend to have what is known as a warm sector. And the warm sector is a region where there's a moist, humid air mass in place that serves as a focus for thunderstorm development. And that's present across much of the state of Mississippi and into western Alabama. So turning over to cold fronts tend to be a significant source of unsettled weather. And basically what these are is they serve as a boundary at the leading edge of a warmer air mass, but basically it indicates the transition into a potentially much colder air mass. Think that, think when you have a temperature gradient that's really large, that indicates a pretty potent cold front. But cold fronts are associated with some pretty unsettled and sometimes severe weather. Generally you will get thunderstorms and squalls with these fronts. Certainly thunderstorms result from cumulonimbus clouds, which there'll be more of a discussion in the advanced section tonight. But ahead of fronts, you'll generally see that winds are more south to southwesterly before the front passes, and then the winds veer more west to northwesterly. Winds can become very gusty ahead of the front too, but they usually, will tend to veer with time as the fronts pass through. And then in this case of what you see on this image, the blue triangles on the front tend to indicate the direction that it's moving. So they're pointing in the direction the front is moving. In this case, it's moving southeastward. And here's an example of a cold front extending from the mid-Atlantic, so New Jersey, down into the interior southeastern United States, across the central and southern Appalachians. And this front is generally moving southeastward to southward, depending on what part of the southeastern United States you're looking at. So cold fronts indicate the transition from a warm air mass to a cold air mass, but the opposite tends to be the case with warm fronts. Usually warmer air masses will tend to overspread cooler air masses. Unlike with cold fronts where you tend to have severe weather and very strong gusty winds. That's not always the case with warm fronts. You can get locally enhanced winds, but it's certainly not nearly as common as it is with cold fronts. But unlike with cold fronts where cooler air masses take hold, the air masses tend to become warmer and more humid as it passes over a given region. And you'll tend to see northeasterly winds veering more east to southeasterly. And in this case, the semicircles also indicate the direction that the warm front is moving. So in this case, it's pushing northwestward. And extending from the Great Lakes across the northern Appalachians into the Delmarva region across the eastern United States, you can see this warm front in place, pushing northeastward into the interior northeastern United States, based upon the direction and orientation of the red semicircles. So stationary fronts tend to be the convergence of cold fronts and warm fronts. When they do converge, of course, one's moving in one direction and the other's trying to move in the opposite. And because they then can't move, they become what is known as stationary fronts. And these tend to serve as a focus for rain. Again, usually you won't tend to get severe weather with stationary fronts, but it's often the case that you will get unsettled weather with these. Potentially heavy rainfall, but severe weather is usually not as much of a concern. You can see in this example, there's a stationary front extending across Kansas and into eastern Colorado. The warm front's trying to lift northwestward, but the cold front's trying to push southeastward. But because these two fronts have converged, there's going to be little in the way of movement with those. So occluded fronts are another type of front that occurs, when you have a cold front that's catching up to a warm front. And what happens is with these, when a cold front overtakes a warm front, you get the occlusion, but that involves warmer air masses being lifted off the ground. It's basically a cold air mass, meeting a less cool air mass, and then the warm air is pushed aloft. But usually, an occluded cold front tends to indicate that the system has reached its mature point, and that from there it will begin to weaken. So, when you're looking for a system to weaken, usually one of the first signs of that occurring is that there's an occlusion occurring, with one of these. So you can see here, the cold front and the warm front are usually moving in the same direction. And in this case, they're pointing upward. So that's a northward moving occluded front. But usually when you think about the direction that, cold fronts and warm fronts move with a system, you'll tend to find that an occlusion will move eastward to northeastward. And it's basically denoted as a hybrid of a cold and warm front along a purple line. So you'll briefly recall that when I first opened up the discussion about surface analyses, we discussed troughs of low pressure. There are similarities and differences to these with cold fronts. But first, basically, they form on the backside of lows, and you can get showery weather. Now, where they are similar to fronts, cold fronts in particular, is that they are associated with a wind shift. And you can occasionally get thunderstorms with them. With cold fronts, you can get severe weather. It's not so much the case with troughs. It's not a zero concern, but and it can happen, but it tends to be pretty rare by comparison. The biggest difference between a trough and a cold front is the fact that there is little in the way of a temperature change, even in spite of the wind shift. And part of that has to do with the fact that the winds may not shift to a more northwesterly direction, but they can shift to a westerly direction. And then when the front comes through, they tend to shift to a more northwesterly direction, which ushers in that cooler air mass. But bottom line, they tend to be similar to fronts in some ways and different in others, in that they do both result in unsettled weather. But fronts tend to be stronger with more severe weather, and there tends to be a more pronounced wind shift and temperature change with them. So in this example, you can see the trough of low pressure extends behind the cold front and the occlusion across southeastern New England and into the eastern Carolinas. And as I mentioned in the first part of the surface analysis discussion, they're denoted by the brown dashed lines. So now that we've talked about surface analyses, there are also upper level analyses, which are important to have an understanding of. The same concepts hold here with upper level analyses that they do with surface analyses, in that when you do see a digging trough, that's usually an indicator of unsettled weather. And then when you see an upper level ridge, that's indicative of favorable settled weather conditions. The reason why these charts are important is because they give the viewer a better understanding of where weather features might be developing. Such features include, but are not limited to, cold and warm fronts, as well as developing lows and gales, as well as areas of high pressure. And you can see that there's a digging upper level trough across the eastern third of the country, east of the Mississippi River Valley. Whereas west of the Mississippi River, there's a large ridge of high pressure. So basically, settled favorable weather in the West Coast, which is often the case, and then unsettled weather further east in this example. When you do look at surface analyses, that you will sometimes find that there are wind barbs. And basically, there's a key difference between wind barbs as well as wind vectors. And it's important to differentiate between the two. So wind vectors basically indicate the direction that the wind is moving. The difference with wind barbs is that they indicate the direction the wind is coming from. So in this example, you can see that we have a wind barb pointing to the west, which indicates that the wind is coming from the west. It's a westerly wind. And you want to take a look at the barbs and the flags on these wind barbs. Whenever you see a full barb, that indicates 10 knots of wind. A half barb indicates 5 knots. So when you add the two barbs together, 10 and 5, you get 15 knots. If we want to convert that over to miles per hour, that would equate to 17 miles per hour. Now, when you go from a barb to a flag, the flag on its own indicates a 50-knot wind or 58 miles per hour. So in this example, the wind is coming from the south and it's at 50 knots or 58 miles per hour. Sometimes you'll find wind barbs that have a combination of both the barb as well as the flags. So you get the 50-knot winds, then you got two 10-knot barbs, 50, 60, 70 knots, and then a half barb that's 75 knots. Converting that to miles per hour, that's 86 miles per hour. So whenever you're looking at a surface analysis, if you see wind barbs, the key takeaway is that it indicates the direction the wind is coming from, not the direction that it's moving. And you might see on some weather apps that wind vectors are present on the maps, but that indicates that the direction that the winds are moving as opposed to where they are originating from. So back in the day, before technology was a thing, there was the Beaufort scale that was developed by a gentleman named Sir Francis Beaufort, that was developed in the early 1800s. Basically, the goal of this resource was to provide mariners with a visual interpretation of wind speed, and you could use the sea state to make those visual references, most particularly useful in the most open waters of the ocean. Of course, in coastal areas, that certainly could be more challenging, especially if the wind is offshore and fetch is reduced, which in turn reduces the sea state. So in that example, that would be a limitation to the Beaufort scale if you wanted to go old school. But basically, the Beaufort scale ranks from force 0 to 12, and you can see that there's various speed ranges with the winds, and then an explanation as to what conditions would be observed within the sea state. So you can see, obviously, force 0, that's basically glass on the water because there's very hardly any wind, if any at all. But as you work your way up in the force scale, you'll note that the wind speeds do increase, and thus the sea state also increases as well. So basically, this was an old school tool that was developed back in the day to help provide that visual of what the wind speed might be just by looking at the sea state. One of the other important and resourceful tools that can be very helpful to a sailor is the barometer. So you remember at the beginning of the talk when we talked about areas of high pressure and low pressure, highs are associated with benign weather, lows are associated with unsettled and particularly rough weather. Well, a barometer can give you an idea as to whether the pressure is changing, whether it's increasing and for the better, or lowering and for the worst. But basically, when pressure is, in the case of decreasing pressure, you want to take a look at how quickly it's decreasing. If it's a slow and modest decrease, yes, it's good to be prepared for incoming severe weather. If it's more rapid, such as 4 to 5 millibar pressure falls in the span of 6 hours, it means that weather is significantly changing for the worse. So basically what happens is, for the 1, 2, 3 rule, immediate action may not be needed if you're on the water to prepare for adverse weather, but you need to be weather aware because it means that weather will be changing. But of course, in the case of a scenario where the pressure is dropping like a rock, obviously you would need to take action on the water to avoid potentially severe weather. Certainly modest drops in pressure occurring over a period of time can mean that a cold front or even a trough are approaching. Slight drops in pressure can also result from warm front passages, but larger drops in pressure over a shorter period of time can mean that there's the presence of a gale or heaven forbid, a tropical cyclone approaching the region. So it's a very resourceful tool to have to better understand how the weather might be changing, and you can have that all at your fingertips by monitoring the changes in pressure. So, with technology these days, the National Data and Buoy Center, for example, does provide a wealth of information through its multiple buoy sites to provide quality controlled information that can range from significant wave height as well as wind, the overall pressure, and the mean wave direction. But it also includes more generic things such as the air temperature and the dew point, as well as the water temperature. But it'll tell you what the mean wave direction is, and the average wave period. It will also give you a timestamp for when that observation was recorded. So like I said, it's quality controlled, so any erroneous data will be removed and filtered out. So, if it's a recent report, you can be assured that, it's up to date and the information is accurate and correct. You can refer to particularly buoy details at a given location. And in the case of on the National Data and Buoy Center, over the span of about 24 hours or so, you do have the ability to monitor and review changes in the pressure, as well as the wind speeds, their associated gusts, and the sea state, but also the changes in pressure itself. So these are obviously very important and very useful for self-weather briefings. Excuse me. And in this case, it's a fairly benign weather scenario. And the reason why is because there's a variable change in pressure, as you can see over this period. It slightly drops, it slightly rises, it tends to remain, unchanged at times. And then you can kind of confirm that with looking at the speeds of the wind and their associated gusts. You can get some blips in higher winds and higher seas, but by and large, you can see that there's really no change in the forecast. So because of the fact that, there's not significant changes in the winds and the seas, you can infer in this example that there's, high pressure, the pattern is stable, and you would not encounter any significant weather concerns. But using these to evaluate what's ongoing, whether there are any significant changes in either direction, can give you a clue as to how the weather might be working in your favor or whether more immediate action is needed. So another resource that can be available, it's not as quality controlled as the buoy data center, but ship observations. Buoys tend to remain stationary in a given location, but one of the drawbacks, in addition to the fact that they're not quality controlled, is that ships obviously change locations. They're underway from one location to the next, so they might be moving in and out of weather systems. They could be moving into a high, they could be moving ahead of a cold front. So those are caveats to take away when you're assessing the reported data on a ship observation. Another concern is that the buoy or the location for the observation might not be located on the part of the ship that's going to provide an accurate reading, because of the fact it might be located on the ship's mast. And a vessel that's already underway is going to encounter higher winds, that high up. So that's something to take with a grain of salt. Certainly a grain of salt is not as necessary with the National Data and Buoy Center, but certainly something to take away from ship observations. But the good news is they do communicate a lot of the same information that buoys do, such as the wind speeds, even associated gusts can be reported, the pressure, the dominant period, the visibility is at that given report, and the temperature of the water and the dew point, as well as the air. Another resourceful tool that you can use is also the advanced scatterometer. So this gives you a bigger picture than buoy data or even ship data might provide you. Basically, how the scatterometer works is that there's a satellite pass that occurs up to 2 times per day that basically scans the Earth, moving from pole to pole. But it can give you a larger overview of the observed winds in a given location, and that is basically derived from the wind-driven seas. So it estimates the wind speeds based on the wind-driven seas in a given location at a given time. So when you're converting winds to wind-driven seas, think that 5 knots of wind is equivalent to 1 foot of wind-driven seas. One of the limitations with this data, and you can see it very clearly in this picture, is that, it obviously doesn't scan every square inch of the Earth, and you will see that there are holes of data. And in this case, you can see that you've got the two ribbons of winds recorded, but then there's blank observations on either side, and that's just because the satellite is unable to get a full picture of every square inch of Earth. So that's something to keep in mind. Another thing too is that it only updates twice a day, so you have to pretty much evaluate the trends to get a better understanding of what's played out and what's going to happen going forward. So moving on to radar, everyone I would think is familiar with what a radar is, and basically it's used to measure the intensity of precipitation. With the intensity of precipitation, it comes in different colors. Cooler colors tend to be lighter and less concerning, precipitation rates, but the darker and warmer colors tend to indicate that it's more intense. And when you see the darkest colors, such as in orange or red, that can indicate thunderstorm development. So you can see here, this darker shading of hotter colors off the coast of Texas indicates that there's likely thunderstorms. And at the very least, it's very intense rainfall. So as far as radars are concerned, across the United States, there are 160 of them. The availability, though, tends to become more variable and limited worldwide. For those, at least here in the United States, there tends to be a 290-mile range with them, with some slight overlap, because of the fact that, if there was not that overlap, some locations would not be able to get necessary radar coverage. And, if there was a scenario where you didn't have that overlap, like think, in the plains, such as Kansas, for example, which is at the heart of Tornado Alley, if there was that lack of radar coverage, then obviously that could be a matter of life and death. So you need to have that continuous coverage from one radar location to the next to make sure that every area can be viewed on radar for any hazardous weather concerns. And as I said, radars can indicate tornadoes and waterspouts. And this is just one example of that. So this type of system, as you can see, moving on shore, this is in Goderic, Ontario, is a classic textbook supercell thunderstorm. And these supercells are characterized by their textbook comma shape on the southern extent of the system. That is where you're most likely to find a tornado or a waterspout. One other way to look at it is you can view it on velocities. And how it works is you want to look for a couplet where the varying colors will meet. So in this case, the blue tends to meet, you can kind of see it in here, the orange and the green basically converge. And what happens is one color indicates that the winds are moving towards the radar. The other color indicates that they're moving away from the radar. So it basically creates this, think of it like a dough rolling effect, if you will. When you take that dough roller to flatten the dough for what you're going to be putting in the oven, it creates that rolling effect. And then when the updraft tips it down into the vertical, that's when you get the tornado. So that's essentially what's happening here. Waterspouts occur on the water. Tornadoes are what is known as a waterspout over land. So any waterspout that has touched down is going to be converting into a tornado as it moves on shore, in this example. So with a bit of a discussion on the satellite imagery, there's multiple forms of satellite imagery, but the overall goal of all of them is to determine sky conditions. Some of the satellite imagery involves visible satellite imagery, infrared satellite imagery, and also water vapor, which is not so much satellite imagery as the former two, but it can give you clues as to where there are troughs and other disturbances in the upper levels of the atmosphere. But in the case of the former two in particular, and the first one in the case of fog, you can also find areas of thunderstorms and other various weather features. One such instance is that of an outflow boundary. Think of that as like a mini cold front, a mini gust front, I should say. You might find yourself out on the water and then all of a sudden you get hit by a surge of gusty winds. Well, there may not be a thunderstorm directly overhead your location, but they can emanate from thunderstorms themselves. So even though the weather appears benign and favorable above you, it can indicate that there are thunderstorms on the horizon, or at least not too far off, even if you're not going to be directly affected by them. So visible satellite imagery provides the highest resolution imagery that you're going to find. And that's also in part because of the fact that, it relies largely on sunlight. Clouds tend to be illuminated by the sun on this imagery, but obviously there's a very significant drawback to that in that you need sunlight to be able to utilize visible imagery. After dark, visible satellite imagery is basically rendered unusable. But because of its higher resolution, you can see the various types of clouds. You can make out the popcorn texture to thunderstorms, and you can find visible satellite imagery on any online websites such as NOAA, as well as the GHCC. They provide a wealth of information that you can use to your advantage. One such resource that I also find useful, schools that have the degree of meteorology also provide these resources as well, such as College of DuPage, which is a university outside of Chicago. But basically, visible satellite imagery is great to find existing structures in the clouds. And here's an example of that. You can see a cluster of clouds over the Leeward Islands and the Lesser Antilles. And if you look closely at them, they kind of look like cotton popcorn textures. But you'll also note these thin ribbons that tend to appear within these imageries. And you can even see it further away from the clusters of storms. Those are what you would find to be outflow boundaries. So those gust fronts basically working ahead of the parent thunderstorms in action here. So, the moral of the story is you don't need a thunderstorm overhead to have gusty winds. When these boundaries work their way outward from the parent thunderstorm, you can get those gusty winds as well. So a little bit more of a zoomed in image off of southeastern Texas. You can see the cotton popcorn-like texture to these clouds, which indicates the presence of thunderstorms. In areas where the cloud cover tends to be more smoothed out, you can likely conclude that that's more stratiform rainfall that's occurring. Could be heavy, but not as intense as what you're seeing with thunderstorms. Visible satellite imagery is also a high resolution satellite imagery that's very useful to find fog banks. In this example, for anyone who might have sailed in New England, you know that the summer months tend to be quite foggy at times, especially when you consider the fact that, the Gulf of Maine, for example, remains very cold even into the summer months. And that temperature difference between the mainland and the Gulf of Maine, in this case, results in a pretty significant temperature gradient. And you can get these pronounced fog banks that develop really at any time of day, honestly, during the summer months. It tends to become less pronounced away from coastal areas, though. But fog banks tend to be smoothed out and tend to be darker, grayer areas. They don't have that same popcorn-like texture that you find with thunderstorms. But when you put a visible satellite imagery in motion, you can see the progression of these fog banks. So infrared imagery basically picks up, has the advantage of finding, being utilized during times of day and night that would not be possible with visible satellite imagery. And that's particularly the case during the nighttime. So infrared satellite imagery, while it doesn't provide, the same overview of cloud structures, it does allow you to measure cloud temperatures. So one of the things that's worth considering with infrared satellite imagery is think of temperature decreasing with height. As temperature decreases with height, it becomes colder. So the colder the cloud top temperatures, the taller the cloud is likely to be. Obviously, as we discuss with visible satellite imagery, there's a major drawback to the fact that you can't view it after dark, but infrared imagery is available regardless of the time of day or night, But the trade-off is that it's a lower resolution satellite imagery, and thus you won't be able to see finer scale features like fog banks or gust fronts. But you can generally see where thunderstorm activity might be ongoing. So in this example, you can see several areas of warmer cloud temperatures, or warmer color temperatures, I should say, warmer colors that indicate taller cloud tops. So in this case, a couple areas stand out as an example, such as the Yucatan the Yucatan Peninsula and Cozumel, and then just south of the Rio Grande Valley. And the colder colors tend to indicate that, there may be rainfall ongoing, but it's not nearly as intense because the cloud heights are lower than their counterparts, in this case, across the Yucatan and the Rio Grande areas. So turning away from satellite imagery, we're going to begin to wrap up this first part of the presentation with a discussion on currents. So it's certainly on its own, it's not a weather-related phenomena, but it's important to have an understanding of how the currents work because it can mean the difference between a successful and an unsuccessful sail. One such example is the Gulf Stream, which we would consider a larger scale current. But of course, there are also smaller scale tidal currents that can occur closer to the coast. And those tend to be more subject to change based on the weather that is occurring. Or even through the phase of the moon. Usually you won't see any significant changes with the current itself, such as in the Gulf Stream when you have a significant weather event, but having it in place can certainly affect the sea state that you are going to encounter. But when you do have a pretty significant system moving across Florida, and for example, gales and tropical cyclones can at least result in some influence, but it's compared to its tidal currents counterparts, the changes tend to be a bit more insignificant. But basically, you can have a high degree of variability in the current speed over a short distance. So here's an example of the Gulf Stream ribboning up from eastern North Carolina into open waters off of the mid-Atlantic and then passing south of the Canadian Maritimes. Basically, what's happening with the Gulf Stream is it's transporting warmer water northward and northeastward. And you'll note here that there's several counterclockwise and clockwise rotating eddies. Basically, a cold water eddy tends to be a counterclockwise rotating region of elevated currents. And basically what happens is cold water is being transported from one location to an area where there's warmer water, and the opposite is true with warm water eddies, where warm water is being transported to cooler locations. But because it's acting as a method to transport that warmer water northeastward, you can see it on full display in this example where the warmest sea surface temperatures are, primarily near Cape Hatteras and northeast of there. Sea surface temperatures are generally on the order of 80 to 84 degrees, and those warmer temperatures are ribboning out into the open waters to the south of the Canadian Maritimes. But further to the north of the Gulf Stream, you can see that the temperature drop-off is pretty steep and significant. In this example, in August, the sea surface temperatures in the Gulf of Maine are generally in the low to mid 60s. So, you tend to have a pretty sharp drop-off with respect to the temperatures, north of the Gulf Stream. So, with that will wrap up the first part of our discussion. And I will turn it back over to Hugh.
All right. Well, thanks, Alex. Really appreciate your presentation.
Of course.
So first of all, are there any questions that folks have that they'd like to ask? And if you can come off mute, if you've got some questions you'd like to ask Alex before we begin to wrap things up.
I have a question.
Sure, go ahead.
Um, I was wondering, I'm sorry, I lost connection a bit in the parking garage at work, so I hope you didn't already cover this. Did we cover the Cape Index?
Yeah, so with respect to the Cape Index, it's not the be all tell all with respect to thunderstorm development, but it's a very strong indicator that there's at least the parameters in place that would be ripe for thunderstorm development. So the reason why it's not the be all end all is because with thunderstorm development, obviously you need a high Cape Index, which is an indicator of significant instability, but you also need a trigger to develop the thunderstorms. So in the case of a cold front, that can serve as a trigger. If you're somewhere like Florida, you don't necessarily need a cold front to trigger thunderstorm development during the summer months, for example. You get the instability, but you also have other triggers such as sea breeze fronts moving in off the coast that serve as convergence zones. So basically, with respect to the Cape Index, to summarize it all up, it's an important component in forecasting thunderstorm development, but there are, of course, multiple ingredients that are needed to go into the development of such storms. If that all makes sense.
Yes, thank you.
You're welcome. Thank you for the question.
Great. Any other questions? Okay, well, we'll move along. If you're looking to, more information about WRI, you can reach them at wriwx.com, which is there in the screen there, and you can get their look at their website and look at their products and services that they offer for sailing and other industries.
Thank you
Um,
so much.
oh, I'm sorry, was somebody going to ask a question?
Oh, no, that was just me. I'm so sorry. I just wanted to thank you for sharing that.
Oh, no worries. And then, part of sailing and boating with Captain Deb, who again, she wishes she could be here, but with her back surgery the other day, I was her stand-in, and but she'll certainly be back on the next weather webinar that we're having in a few months. Some of the things that are offered through Sailing and Boating LLC, there are some online courses, flashcards, cruising courses. One of the important, it's a really great class, is the Women's Sailing Retreat. And the idea is that my wife takes 2 or 3 women on a week-long sailing in Grenada. And the idea, is to just spend that week learning about sailing and managing a boat. And it's a great way to understand about what cruising is about, what things you run into. You'll certainly run into problems. You'll get a lot of great sailing because that part of the world is essentially a beam reach all the time. And so you sail north and south and there's some great sailing. And you can always get your weather report when you're in that part of the area there too. And then also things like cruising couples instructions. If you're a couple or you have a partner and you're looking to go out cruising, there's a lot to know about how to do it. It's a very different thing than racing sailing versus day sailing. Cruising, on a boat, it becomes your home for many people, and so there's a lot of information that can be really helpful to learn before you go out there. And then, Debbie also will take couples out there and people and show them, how to do it. The next women's retreat is in March, but that is completely full. The one after that is on May 2nd through 9th of next year in Grenada. So it will start in St. George's and they will sail north up to as far as perhaps Bequia, if anybody is familiar. But those islands are each about 20 miles apart. So you kind of get an open crossing, and then you get Windward and Leeward Island sailing as well, plus as anchoring, plus mooring experience. It's really a great opportunity to get some firsthand knowledge. And then moving on. We just want to thank everybody for showing up. I want to thank Alex for doing the presentation. There is another webinar on January 7th called Comfortable Cruising. And this is something that a lot of people have found very useful. Some of you may think of cruising and, well, it's a small boat and, it's going to be difficult and sort of difficult like camping. And in this webinar, Deborah talks about, what are the things that you should really have on a boat? What things make a difference? Things like water makers and solar and lithium and the whole approach to cruising so that you're comfortable, that you're really enjoying it, not just surviving out there. And if you go to the Sailing and Boating LLC website, there's a coupon code here that you can enter, and then you can attend free of charge.